With my research, I try to get a better understanding of physical phenomena that are not supposed to happen under normal circumstances. One of such phenomena is superconductivity, where electrons paradoxically form pairs even though they repel each other, resulting in a complete absence of resistance. This means that all the current that goes into one end of a superconducting material comes out at the other end, which for applications is a dream scenario as there are no losses. Unfortunately, superconductivity generally takes place at very low temperatures, below about -250 degrees Celsius, making it hard to use in everyday life. However, there are a few superconductors that operate at much higher temperatures, although they are still low for practical purposes. The idea is that if we can understand what causes the electrons to pair up in these materials, we might be able to engineer superconductors with even higher operating temperatures. To reach such deeper insights, I directly study the individual atoms and electrons and how they interact using the scanning tunneling microscope that I built here at the LPS. The microscope consists of a sharp needle that is placed so close to the surface of a material that electrons can jump across the vacuum gap, leading to a tiny current, typically 100 million times smaller than the current through a light bulb. By moving the needle across the surface, the current is then used to extract information about individual atoms and the electronic properties of the material. The tricky part is that the position of the needle needs to be controlled with atomic precision, requiring vibration isolation, soundproofing, and very sensitive electronics. What distinguishes our instrument from others is that we can not only measure the tiny tunneling current, but even the fluctuations in the current caused by individual electrons, using specially designed circuitry. These current fluctuations provide even more insight than the average current in how the electrons interact with each other, which is essential, for instance, to understand why they pair up in superconductors. Using this novel technique, we found that specific atoms in one of the high-temperature superconductors are trapping electrons from time to time, and that the electron pairing seems strongly influenced by the position of bismuth atoms in this material. Both of these findings help us a step closer to a microscopic theory for the pairing mechanism. For me, the beauty of this research is that every day I'm directly looking at the building blocks of matter and do it with an instrument that I glue together myself. You can see beautiful structures and patterns, but also imperfections and impurities, all of which combine to make the material as a whole behave in unexpected ways, and it's up to us to figure out how.